video we're going to talk about the photoelectric effect performed by Albert Einstein. So at this point we know that light can exist as waves. We've seen that through the double slit experiment, which definitely showed that light has properties of waves. Einstein also argued, however, that light had properties of particles. So he used this photoelectric effect experiment to demonstrate that nature of light. So wave theory predicts that only the total amount of energy transferred by the light to the metal will determine whether electrons get ejected and what energy they have once they get ejected. And that's because light, thought of as a continuous wave, if you have the intensity is basically how bright the light is, and then we know that the frequency, the higher the frequency, the more energy it has. So that implies that a high intensity of a low frequency light, like red light would be low frequency, could have more or about equal to a lower intensity violet light. So the total energy would be all that matters, and under those conditions you'd essentially get the same amount of energy with the electrons that are coming off. So light shines on the metal, electrons get ejected, and all that would matter according to the classical physics theory, the wave nature of light, would be the total energy being applied. The particle theory, however, predicts that the light comes in these little quantized chunks, or little chunks of packets of energy, and that those little chunks, the energy of those would be dependent on the frequency, just according to Planck's equation, that energy is constant times the frequency. So that only the frequency would determine whether or not electrons get ejected and the energy with which they get ejected. So we're going to just mess around with this and we'll take a look at a couple different scenarios. So we can see that when you're shining any intensity of violet light, you get electrons ejected, whether it's low intensity, it's just less of them, or high intensity, and where you have more electrons ejected. Okay? However, if we go to red light with a low intensity, you get no ejection of electrons. Now, classical physics would predict that if I crank up the intensity of this red light, I'm going to get the electrons ejected, and the higher the intensity, the faster they're going to come off. And what you see is that you get nothing. So essentially there's a minimum threshold of frequency that's required to eject the electron. That shows a particle nature of light. If you picture an atom with an electron moving around on the outside, if the light hits it, it's that individual whack from the photon that's going to make the electron get ejected. And the stronger that photon whacks that electron, the faster it's going to come flying off. And we're going to see that in this part. So if I crank it up to a violet light, we'll see that we get those electrons ejected. So we've reached that minimum threshold of energy required to eject the electrons. And now we'll see that if I crank the frequency up to really high levels, like if we get into the UV light spectrum, you can see that those electrons are ejected with a much higher velocity, right? So what that showed is that once it hits it hard enough, any additional energy, once it's overcome that energy required to eject the electron, is going to be converted to kinetic energy of the photons being ejected. So you have more energy on the electrons that are getting knocked off. Okay? And what we also learn is what the intensity really represents of the light is how many photons are being emitted. So a low intensity light or a dimmer light will just have less photons being emitted. A higher intensity light has more photons being emitted.